you won't mind, I will briefly introduce Paolo Personnettaz. He recently defended his PhD, in fact, a few days ago, if I remember well. I really would like to thank him for accepting this invitation. He actually works at the Helmholtz-Zentrum Dresden, Rossendorf Institute of Fluid Dynamics, as you can see in his presentation. So, Paolo, thank you very much again for accepting this invitation, and feel free to start. Go ahead.
Thanks a lot for the introduction. So I will present my work on transport phenomena in liquid metal batteries. It's mostly based on simulation. And my supervisors at Helmholtz-Zentrum Dresden Rossendorf are Dr. Norbert Weber and Dr. Tom Bayer. And at TU Dresden is Professor Kerstin Eckert. And this work was also done with multiple collaborations. And I will present talk about the collaborator during the talk. So I will first introduce a bit the topic, and in particular the state of art of the study on mass transport in liquid metal batteries. This is the main transport phenomena that I will discuss across this presentation. Then I will use a quantitative analysis of an experiment to discuss the role of mass transport together with the numerical simulation of solutal convection. At the end, I will also discuss about the role of the coupling with the molten salt electrolyte. Can I could you see the mouse or not? I just this worry.
Yes, we can see your mouse.
Okay, I was worried about the mouse. Yeah, I will restart the outline. So I will introduce and discuss mass transport, and then I will use an experiment and numerical simulation to discuss what is the role of mass transport in the different phase of operation of the battery. And in the last part, I will talk about the role of the molten salt, of the coupling with the molten salt electrolyte. So we look at electrical and mechanical coupling with the layer. And at the end, I will conclude with the result. In order to allow the penetration of intermittent and renewable energy sources like sun and wind, we need electrical energy storage that should be cheap and reliable. And in order to be cheap, we need a technology that has a long lifetime, simple construction, and use inexpensive materials, and also high power densities of great interest. And liquid metal batteries are able to meet all this demand. In particular, the liquid nature of the cell allows simple construction. We have 3 layers that are stably stratified by the density differences. And we have a long life due to the liquid nature of the electrode, and high current density due to the liquid nature of the interfaces and the high temperature. And at the same time, we can select specific material in the periodic table that are at the same time abundant and inexpensive. So on the top, we have the negative electrode. This layer is done with the metal of the first and second period of the column of the periodic table, like lithium or sodium. In the mid, there is a molten salt electrolyte that is able to conduct the ions of the negative electrode metal. And in the bottom, we have an alloy that is made from a solvent that is a metal of this region of the periodic table, like lead or bismuth, and together with a metal with the metal of the negative electrode. And the alloying of the positive electrode is the technique that we use to store energy inside this electrochemical cell. So understanding mass transport in the positive electrode is of great interest. So I will look fast at the operation of the battery. So during discharge, we have the oxidation at the negative electrode electrolyte interface. Lithium ion are conducted through the electrolyte, and then we have a reduction in the positive electrode electrolyte interface. And during charge, we have the opposite. So the we have a purification of the positive electrode. So we remove lithium from the positive electrode. The lithium ion are crossing the electrolyte, and they are reduced at the negative electrode-electrolyte interface. And now it's important to focus in the operation, what is the role of mass transport? And in particular, we can first notice that concentration, and so mass transport is important in the positive electrode, because the equilibrium cell voltage of the cell is a function of the concentration at this positive electrode-electrolyte interface, that in the following we just refer as interface. And the equilibrium cell voltage here is computed with the Nernst equation. We have over voltages. This means inefficiency if the concentration at the interface and the concentration in the bulk are different. And here, this is the formulation of this over voltages that are referred as mass transport over voltage. This means that we have a non-ideal condition if the interface and the mean concentration are different. And the third important point here is that we have a mass flux imposed at this interface. This mass flux is dictated by the Faraday law of the electrolysis, and it's directly proportional to the current density applied in the cell. Mass transport was studied only by a few authors, but in the first investigation already in the 60s, we know that concentration polarization is important, and it takes place in particular at the positive electrode-electrolyte interface at high current density. This concentration polarization is just another name for the mass transport over voltage that we discussed in the previous slide. And this takes place at a high current density and during discharge. This means that there is some difference between charge and discharge, but no one was able to explain it. More recently, in the PhD thesis of Newhouse, a diffusion model was used to study the voltage evolution in the liquid metal batteries. And later, Barriga and Hashor and Kelly used an advection diffusion model to study the transport of the concentration inside the positive electrode. This model used a fixed velocity, and therefore it is missing the coupling that there is between mass transport and fluid dynamics, and this coupling is thanks to buoyancy, as we will discuss later. So we have two goals. We have to solve these two missing points in the following part. And to do that, in particular, the first point, we look at an experiment, and in particular at the over voltage differences that are between charge and discharge. So the experiment was designed and run at the HZDR liquid metal batteries laboratory by colleagues. And here a photo of the experiment. So on top we see this spiral that contains lithium. Then the transparent fluid that we see here is the molten salt, and below there is the positive electrode that we cannot see. Here are schematics of this cell with the 3 layers. The experiment is run under an amperostatic condition. This means the current is imposed and the cell voltage is measured. So we see here, current is at the beginning 0. Then we have a charge phase. Then again, the current is set to 0, a discharge phase, and again a quiet phase with no current. And here is the dotted line is the recorded voltage. During charge, we have this oxidation at the interface. This means we remove lithium from the lithium bismuth alloy in the positive electrode. And what we observe is that if we compare the experimental voltage with a simple model that considers only the equilibrium cell voltage computed with the mean concentration and the ohmic over voltage, that is the voltage drop due to the resistivity of the electrolyte, we see that these two quantities are able to perfectly match with the experiment. The red line is the sum of the two terms, and and the dotted line, the black dotted line is the experiment. And from this result that the interface concentration, the mean concentration are the same. This means that there is some mixing in the positive electrode, but we need a model to understand it. And this mixing can be explained by the fact that we are removing the light fluid from the top of a heavy fluid. We locally generate heavy parcel of fluid that then sinks down and generates a strong flow that mixes everything very well. During discharge, we have the opposite reaction. So we are depositing light lithium on top of the heavy alloy. This is a stable condition because we are depositing the light over heavy. And if we just use the equilibrium cell voltage and the ohmic over voltage to model our experiment, we see that the red line is not able to capture well the black line. There is some additional over voltage, and this is the mass transport over voltage that we discussed previously. So there is a difference between the interface and the mean concentration, and we need a model to define the interface concentration. And we will use diffusion to model this part. Why? Because we have a stable stratification, stable density stratification, and this results in no flow. No flow means that we don't need to solve any Navier-Stokes equation, and a simple pure diffusion model is sufficient. And we solve it with analytical methods and find a different solution. And here we see what is taking place. So we are introducing light lithium from the top. And these are the concentration profile and how they evolve in time. We are really interested in reality in the evolution in time of the difference of concentration between the interface and the mean, because this is a measure of the mass transport over voltage. And with the simple model, we can see that this scales as a square root of time minus time. And it's also important to see that the interface concentration scale as the first power of the current density, and therefore also the mass transport over voltage will follow this scaling. Now, if we take the previous model and we plug it inside our mass transport over voltage equation, we see that we are able to capture extremely well the experimental behavior. So the three contributions, the equilibrium, the ohmic, and the mass transport are able to describe perfectly what happened in the experiment. They are also able to describe the following transient. So when the current is shut off, there is a concentration profile that has to go to the homogeneous distribution, and this is what we see here. So diffusion over voltage is required during discharge. Now we invert the previous equation and we now compute the interface concentration here as in the form of a molar fraction. At the beginning, we have a uniform concentration, and then we have this charge phase. If you look at the charge phase, we see that also there is a small, a really short in time, only 10 seconds over 30 minutes of experiment, diffusion phase, in which the concentration evolves quite like diffusion. And then the concentration difference set to a fixed value. So we have a very small concentration difference that is present during the charge phase. Instead, during discharge, we have a very large concentration difference with respect to the mean, that is the gray line. So the blue is the experiment, the interface, and the gray is the mean. And if we just compare with the square root of time scaling that we were expecting for the interface concentration, we see that, yeah, this lie perfectly on a line. So now we will move to charge and try to understand what is taking place here at the beginning of the charge phase. And to do that, we need to model solutal convection. So we need to couple a mass transport and fluid dynamics through buoyancy. So we solve incompressible Navier-Stokes in the Boussinesq approximation, including these additional terms that takes into account the buoyancy. So this is the solutal expansion coefficient, and this contains the concentration field. And then we also advect and diffuse the concentration field. We impose at the interface this mass flux as discussed, and the lateral walls are assumed to be impermeable, so no lithium can leak from the lateral walls of the electrode, and all the interfaces are assumed no slip. And yeah, we will relax this condition for the interface with the molten salt later. Yeah, it's important to say that now we are only focusing on the bottom layer of the battery, so we are only studying the positive electrode. And to solve this previous problem, so the Navier-Stokes plus advection diffusion of concentration, we cannot proceed analytically. We need to use a numerical tool, and we adapt two solvers, OpenFOAM, that is based on finite volume, and Semtech, that is a Fourier spectral element code. And we cross-compare this with another code that uses spectral and finite element that is named Svemans, and this was done thanks to the support of Sabrina Benard that was referred at the beginning. And we compare so the solver is used by the group in France to study liquid metal batteries, and here in Dresden the experience was mostly with OpenFOAM, and I also introduced this Semtech that is a spectral code, that is spectral element code. So and we studied the axisymmetric approximation, the lithium bismuth electrode that we discussed at the beginning from the experiment. So here we see the concentration evolution in time. At the beginning, we have the diffusion as discussed. So we have first diffusion transient, and then convection sets in, and there is a deviation from the diffusion. And what we observe is that the four different solvers have different onset time. And the different onset time can be explained by the different amount of noise generated during the solution. So OpenFOAM is characterized with a lot of noise, so the onset takes place earlier. Instead, the Semtech code, that is a spectral element code, is characterized by less noise. And so this noise effect explains the differences here. Later, during the pseudo-steady state, the three solvers converge to a similar pseudo-steady state evolution. And if we compare now concentration and the velocity distribution, at the same time, we see that the structure size is similar across the three solvers. And yeah, the phenomena looks quite similar. So this means that we have a good agreement between the three approaches. Of course, the effect of noise determines where plume starts and the onset as discussed. And as a final point from this comparison of the three solver, we realize that Semtech is 10 times faster than OpenFOAM. So now I move to the part of numerical simulation of solutal convection, and we will start with 2D axisymmetric domains. First, it's important to discuss a bit how solutal convection works. So we are removing the light component from the top of the positive electrode, and this generates these profiles. These profiles are still in pure diffusion as the one that we saw for the discharge. And here we see that on top we have a heavier fluid, so the density on the top is larger than in the bulk. And this results at some point to convection. And so convection is starts from a non-linear and time-dependent phase state. So it's not like the classical Rayleigh-Benard convection in which we have like a straight line from the top to the bottom, but these profiles are really non-linear. And already from looking at this plot, we can see that there are two regimes expected. One at lower times for a very thick layer. We expect that convection starts when the concentration disturbance has still not reached the bottom, and one for very thin layer, in which we expect that convection starts when the full layer is involved by the full layer as a nonlinear profile. And so if the onset time is lower than the time to reach here the bottom of the layer that can be computed analytically with this formula, convection starts in a thin boundary layer. And instead, if the onset time is larger than this time, convection starts in the full layer. So we expect at least 2 regimes at the onset. So what are the parameters that describe solutal convection in this configuration? Yeah, I will first come back to this image. This type of convection is not limited to mass transport. There are also other phenomena. If we imagine to impose a cooling here to a fluid, we have a very similar phenomena. Other phenomena in nature like evaporation and sublimation generate nonlinear profile very similar to the one that we observe here in charge of a liquid, during charge of a positive electrode of a liquid metal battery. So this phenomenon is quite general. And so what are the parameters that describe the phenomena? The first parameter is a Rayleigh number that differs a bit from the classical Rayleigh number that we see in the classical Rayleigh-Benard convection. So we don't have here a temperature difference or a concentration difference, but we have this function of the mass flux at the interface. So this is a concentration difference computed in the assumption that the mass flux across the layer is linear. This overestimate a lot the concentration difference is even larger than the one that we observed during diffusion, but it's important to parameterize the problem. So the Rayleigh number in some way will be our forcing parameters, and it will contain the current density inside. It will be a linear function of the current density. The second important parameter is the Schmidt number that contains the ratio of the momentum and mass transport diffusivity, and then as well the aspect ratio of the cell as a whole. What are the output? So from the application, we are interested to know the mass transport over voltage, so the concentration difference across the layer. And this can be casted inside this Sherwood number that is at the end the ratio between the linear concentration difference and the actual, the one measured from the simulation, or if you do an experiment from the experiment. And the second parameter of interest is for mixing, so it's the velocity. And in this case, we use the Peclet number as a relevant dimensionless parameter that contains inside the velocity in the layer. So to study the problem, we start from a 2D axisymmetric lithium lead electrode because we know very well the material properties for this alloy. They are well known due to the other application of this alloy. And yeah, we study 0.1 ampere per square centimeter configuration that is really in the regime of interest. And this is this Hay letter. And then we change the diffusivity, the viscosity, and the current density, and in order to do a parametric study. And we collect all these different points in the parameter space, flux Rayleigh number, Schmidt number. And we also tested a case in which the height is 1/5 of the height of the layer. So we assume for the reference case 5 millimeter, and these J cases are with 1 millimeter. So very thin layers. And this allows to cover a very wide parameter space that is also useful for other alloy used in liquid metal electrodes. And as discussed before, we expect to see 2 regimes, and we find out that the regime change takes place at the flux Rayleigh number of 3 to the 10 to the 5. And so we have a high Rayleigh number in light green here and a low Rayleigh number regime in dark green here. And yeah, we will first look at the high Rayleigh number regime and how it evolves in time. And we also studied this first studies in 2D, so axisymmetric simulation in 2D, and then we move to 3D simulation, and we study this black and the blue A and J configuration, so at 2 different current density. This is to confirm that our 2D axisymmetric simulation are capturing what the phenomena sufficiently well to study how solutal convection evolve in 3D. And we will both analyze these 2 conditions later. So solutal convection in 2D domains. And we are here is the reference case that I discussed before. It starts with diffusion. So we have negligible velocity and the concentration evolves as pure diffusion. And here we see very parallel line in the concentration field. Then we have the onset of convection and we see this wavy pattern that reminds some Rayleigh-Taylor instabilities. And this detectable perturbation then leads to the first events that are these plumes that are going through the domain. And the effective advective transport here is able to reduce the concentration difference and to accelerate and the penetration generate this strong acceleration in the flow. Then the maximum velocity is reached. The full layer is now involved by the phenomena of solutal convection, and we reach a plateau in the concentration. Instead, the velocity then decreases, so we have a deceleration transient, and then we move to a steady state condition in which the global quantity oscillates around the mean value. This oscillation can be explained with this simple phenomena. So the concentration difference, for example, decreases. This decreases the buoyancy term in Navier-Stokes that reduce, so the buoyancy forcing, this reduce the velocity, that reduce the advection. Less advection means that larger concentration difference are established, and then this more buoyancy, acceleration of the flow, more advection, and resulting less concentration difference in the layer. And of course, diffusion plays a role here, and it smooths out. So we don't have perfect oscillation here. The oscillation are follow a relatively complex time evolution. So now we want to study the effect of current density on these profiles, on this concentration and velocity profile. And what we are doing here, we are increasing the concentration from the blue line to the purple line. And what we see is that the onset, the dot, takes place earlier. The concentration difference is larger, and also velocity are larger. So in the bottom, we have the velocity. And if we look carefully at this curve, we see that there is a good resemblance across the curve. So there is some self-similar phenomena or some similarity going on. And from theory of thermal convection over a heated plate, we know that there is a scaling that in the literature is referred as inner scaling. This inner scaling is practically a balance between diffusive forces and the buoyancy part. And this inner scaling practically works with the assumption that the height of the layer has no influence in the phenomena that we are observing at the beginning. And from this, we can derive a time scale. We can rescale with this, using this inner scaling, both the concentration and the time. And we see that all the curve collapse on a single curve. This means that this inner scaling is well able to describe what is taking place, in particularly at the onset. We see that the onset, it's now just a constant multiplied by this time parameter, this time scale. And if we study the onset of all the simulation, all the configuration of our parametric study, we see that in the light green region, that is at high Rayleigh number, we have a -1/2 exponent, and this confirm as well. It's confirmed as well by the inner scaling. At low Rayleigh number, we have this phenomena that convection starts from the full layer. So we have a different exponent, and we also can see the difference between the high and low Rayleigh number regime by this line at 0.08. This is the dimensionless onset time as rescaled with the diffusion time scale. And this 0.08 is what we saw a few slides before. And now we study what happened in the low Rayleigh number regime. So in the low Rayleigh number regime, convection starts in the full layer. It's characterized by these very large structures that are relatively laminar, I would say. So the blue line is the low Rayleigh number, and we see that the velocity, we don't observe any oscillation compared with the like high Rayleigh number case. And the inner scaling is no more adequate to describe this low Rayleigh number regime. Now we proceed with Sherwood scaling. So as discussed before, Sherwood scale, it's really important for the mass transport over potential. And we find a good, all the result lies on this line in the high Rayleigh number regime that correspond with 1/5 exponent. And this 1/5 exponent, it's correspond at the end to that the concentration difference spells as the 4/5 exponent of the current density in charge. In this charge, we saw that it scales linearly with the current density. And this exponent agrees very well with the one proposed in Hermann et al. In 2020. And this is very relevant, as already discussed, for the computation of the mass transport over potential. So if someone knows the material properties of the electrode, the current density at which it's running, then it can simply, with this correlation, compute the Sherwood number, and then, from the Sherwood number, compute the concentration difference, and from the concentration difference, compute the mass transport over voltage. And for the Peclet scaling that is related to the mixing, we also find a 2/5 scaling of the flux Rayleigh number that correspond in this case to a current as well of 2/5 that agrees as well with Hermann et al. And went back. And this allows again to compute, knowing the correlation, we can compute the velocity inside the layer and know if, for example, solutal convection is able to affect the interface, or which magnitude of flow drives inside the layer. And now we move to 3D electrode. So first we want to check the validity of our 2D axisymmetric approximation. And we see here the continuous lines are 3D simulation and the dotted line are 2D simulation. And we observe a very good agreement between both in the concentration differences and in velocity. And but if we look at for example, if we look at this point at the maximum here of this curve, we observe that the concentration distribution at the interface is not at all axisymmetric. So, but we can explain this agreement, if we look at the evolution. So at the beginning, at the onset of convection, we have this pattern forming at the interface of the electrode. And this pattern is more or less like the wavy pattern that we saw in 2D, but now in 3D. So with the formation of these vermicular shapes. And then we have convection sets in, and we have these very nice plumes, and the formation of this tessellated pattern at the interface. And the plumes per se, the single plume is axisymmetric, and this is what seems to explain the good agreement with the axisymmetric case. So the full flow is not at all axisymmetric, but the single component, it's axisymmetric. And if we go to the pseudo steady state, this tessellated these cells becomes larger, and the full layer again is involved by the phenomena. And this agreement between axisymmetric and 3D simulation with this motivation of the plumes was already discussed in numerical simulation of Rayleigh-Benard convection at high Schmidt number. That is very similar to the condition here in which we are at high, Rayleigh-Benard convection at high prime number, and very similar to what we have here that is at high Schmidt number. So what we discussed up till now is the liquid metal electrode, and I would just to go back to a bit of motivation. And this liquid metal electrode that we have in liquid metal batteries is not unique of these cells, and it takes place also, it is present also in other devices, like in aluminum electro-refining cell when aluminum copper alloys is purified, and also there, we expect phenomena like the one discussed until now, and as well in E2 power conversion, where it is used to purify this alloy, and yeah, so the liquid metal electrode is not only of liquid metal batteries, but what we learn in liquid metal batteries can be extended to electrometallurgy and also to power devices. And now I want to focus a bit on the coupling between this electrode and the molten salt electrolyte. So in the last part, we will study the interaction with the molten salt electrolyte, starting from electrical coupling. So if we look at our experiment here, we see that the negative electrode has a smaller diameter than the positive electrode. So this means that we will not have really a uniform current distribution at this interface. And we can compute the current distribution inside the electrolyte. So now we focus on the electrolyte, just solving the Laplace equation for the electric potential. And this is the result. So this is the electrolyte layer. We assume uniform potential at the top and bottom interface, and the lines, the white lines that we see here are the current lines. And so we have this blue line as a current distribution that is different from the uniform one that we have assumed until now that we assume until now. And this non-uniform current distribution in charge result to a non-uniform concentration distribution. So we have more lithium concentrated here in the core of the cell and less on the side. So the dashed line here is with uniform concentration, and the continuous line is with non-uniform current distribution. And what happened during what is taking place during charge is slightly different. So during charge, we have solutal convection, and solutal convection starts earlier in the center of the electrode, because there we remove more efficiently lithium. So we have some difference at the beginning. The onset takes place earlier in the non-uniform current case than in the uniform, as we also see from this evolution of the concentration difference. But later in the steady state condition, solutal convection is able to smooth out all the differences that the non-uniform current distribution is leading to. And now I would like to focus on a slightly different effect, and this effect is the mechanical coupling of the positive electrode with the electrolyte in particular in the other layer. So we study in this case solutal convection in the positive electrode, and we also solve fluid flow in all the other three electrons. To do that, we use open foam with a multi-region approach. And at the interface, we use an explicit coupling of the interfaces. So this means that we are coupling stress and the velocity at the same time. And what we see, and we validated this code with the solving mass transport in the with Semtech as did before, and also with heat transfer in the 3-layer to study that the coupling works well. I didn't discuss here, I don't want to discuss here heat transfer, but we compare it with a similar code that is pseudospectral from a colleague. And we in order to be sure that the coupling it's working well with our multi-region approach in open foam. And if we look what solutal convection is able to do in the other layer, we see that solutal convection is able to drive a strong flow in the positive in the electrolyte. So not only the positive electrode, but the electrolyte is now mechanically coupled, and flow is generated there. And a weaker flow also is transferred to the negative electrode on top. So we have a momentum transfer across the layer. In this simulation, we are not solving heat transport, only solutal convection in the bottom layer and mechanical coupling and fluid flow in the other layer. And if we look at the evolution of the concentration differences, before we study everything with a rigid layer here, with a rigid and no-slip boundary condition. But if we include the coupling with the molten salt, we see that the actual concentration difference in the layer are smaller. And this is due to the fact that better mixing is allowed by this mechanical coupling. And so future model should include the coupling with the molten salt and with the molten salt layer. So to conclude, with the experiment that I showed at the beginning, we were able to explain differences between charge and discharge. So during charge, we have unstable stratification and small and time-independent mass transport over voltage. And the stable stratification instead takes place during discharge. And this is resulting in a growing mass transport over voltage that can be well described by diffusion. So we include for the first time solutal buoyancy inside our model, inside mass transport model. And we use 3 different approaches: OpenFOAM, Semtech, and Svemans. We discover 2 regimes of solutal convection, one at low flux Rayleigh number that is characterized by a global flow that starts in the full layer, and one at high flux Rayleigh number that is characterized by a thin diffusion boundary layer, and where plumes are present. And we have the scaling with this 4/5 and 2/5 power for concentration differences and velocity respectively. We also study solutal convection in 3D electrodes, and we see that they agree very well with 2D axisymmetric, but the dynamics is not at all axisymmetric. We have very nice plumes and polygonal shapes cells evolving at the interface. We also show that in reality, in liquid metal batteries, in application, the current distribution is not uniform at the positive electrolyte interface, but this affects mostly discharge, and solutal convection in charge makes the effect of non-uniform current distribution secondary. And we also study what happens if the positive electrode and the electrolyte are mechanically coupled. And what we saw is that solutal convection drives a strong flow in the electrolyte, and the coupled interface allows better mixing than no-slip one assumed in the first part of the study. And with that, I would like to thank you very much for your attention, and I'm done.
Great. Thank you very much for a very nice and detailed presentation. We just in time, so we have enough time for questions and comments. So colleagues, feel free to ask.
Alberto, can I ask a question, please?
Yes, please, Professor Ramos.
Paolo, thank you very much for your presentation. It was very interesting and informative. I don't know if I missed something at the beginning, but I would like to understand a little bit better. If I have the correct physical picture of the phenomenon, you would have simultaneous convection due to thermal effects and solutal effects. It would be kind of a two-way possible convection. First of all, am I right in thinking it in this way?
Yes, you're completely right. However, the concentration differences and the temperature differences, and I mean, if one computes the density ratio, so the ratio of the contribution of the buoyancy due to thermal effect and due to solutal effect, it is it is really in favor of solutal effect. So solutal effect are way stronger than the then the thermal effect, and this is practically due to the fact that its sources are not sufficiently strong. The diffusivity are really different, so we have very high diffusivity of heat in the liquid metals and a very low diffusivity of the concentration in the electrodes.
So you would have two Rayleigh numbers, a thermal Rayleigh number and the mass Rayleigh number.
Yes, that's true.
And what you're saying is that the mass effects are far more important than the thermal effects.
Yes, I mean, we study both together in a paper that I didn't present because the presentation was really focused only on mass to not make everything too heavy to follow. So I really just focused on the mass in this case, but we have a paper in which we use the multi-region solver that I discussed before, and we solve mass and we solve heat transfer in the 3-layer and heat and mass transfer in the positive electrode. And what we observe is that, for example, during discharge, so we have some internally heated convection in the electrolyte, but this is not able to affect the concentration distribution in the positive electrode.
Not even when you consider this mechanical interaction? Yeah,
not even when you consider this mechanical interaction. The stable stratification in the positive electrode is extremely, it's very strong. And so there is no chance for, of course, we test only one material, and there are material in which, we have a bit slightly, for example, if the two metals are, in this case, we use lithium bismuth, the two metals are very far away in the periodic table. They are very different mass. And this means that mass transport is very important. If one consider, for example, two metals that are a bit closer in the periodic table, then we cannot rule out a priori the coupling between mass and heat transfer. But in the positive electrode, this is what we usually one can assume. So and we also simulate solutal and thermal together, and we also saw that that usually what you have is that you have a strong heat generation here in the electrolyte and a stable profile here, and the flow practically due to solutal convection makes very well this stable profile, making the temperature distribution in the layer almost uniform.
Yeah, it will make it the lower part even more stable. The
Yes.
thermal effect. Okay. Well, thank you very much.
You're welcome. Thanks.
Yeah. More comments? We have enough time. I have one question. It has been reported in the literature that at the interfaces, there is the generation of an electrovortex flow due to this bending of the current distribution of the electrical potential. When you talk about this non-uniform current distribution in the simulations and for the 3D layer system, did you perform 3D simulation, or will it be important to consider the effect of a rotationary flow near the interfaces? What do you think?
So in this case we didn't practically include any magneto-hydrodynamics effect, but there are there. So this is like a case in which we consider the coupling of the transport in the electrolyte and the coupling of the transport in the electrode, but without considering any magneto-hydrodynamics phenomena. So here probably there will be some weak electrovortex flow generated by this non-uniform current distribution, and in that case 3D simulation are usually required. But here we limit our study to 2D axisymmetric simulation, because for mass transport in this case was what we could do with OpenFOAM in particular. Because 3D simulation are very expensive with OpenFOAM, with the diffusivity and the cell size that is required for resolving solutal convection. So we study solutal convection in 3D only with Semtech.
So it seems that based on your results, you will obtain probably another effect. And I mean, for some of the simulation, you use no slip condition, and then you consider a coupling between the layers, right? And you observe some variation of the solutal convection. So probably for a rotational flow or an electrovortex flow, these solutal convections will be affected, right? What do you think?
So we study solutal convection and electrovortex flow in a paper with the colleagues in Paris. So this Herman 2020 that I was referring during the presentation. And what we observe is for the classical electrovortex flow, so the one in which there is no external magnetic field applied, so no PZ. The solutal convection is again the relevant phenomena, and it is it is able to mix very well the layer, but there is a following studies from the group in Paris as well, in which they include the BZ and so on, also the effect of an external magnetic field, and there is a competition between the two effects, and probably at high magnetic field there is even there is a competition, and at electrovortex flow can also become stronger than the solutal one, the solutal effects.
Thank you.
But only with the current only with the non-uniform current distribution, let's say, that naturally emerge from the battery. The electrovortex flow is relatively weak.
Thank you. More questions? For the experimental prototypes, what are the expected Rayleigh numbers based on these definitions for the solutal convection? Do you have some idea?
So the expected Rayleigh number is in the order of 10 to the 7, I would say. So but I have to stress that this Rayleigh number, 10 to the 7, 10 to the 8, but I have to stress that this Rayleigh number is difficult to compare with the Rayleigh number computed with the Rayleigh-Benard convection, because it contains inside, as I discussed, this linear. Yeah. So you should multiply the Rayleigh number by the 1 over the. So you have to divide the Rayleigh number by the Sherwood number, and then you get more or less a Rayleigh number comparable with the one of classical Rayleigh-Benard convection. So if you have 10 to the 7, you divide by 10, so it's one order of magnitude less, so 10 to the 6 or something like that, to compare it. But okay, this is the full range. If you are at very high current density, you can even get higher.
Thank you.
Yeah, welcome.
More questions maybe from the audience? Also feel free to write in the chat. No. We are just on time, so there are no more questions. So I think we can thank you again for this very detailed presentation. Yeah, thank you very much.
Thank you very much for your attention.
Yeah, thank you, colleagues, for joining us today, and I will keep you informed about future seminars.
Okay, thanks.
Yeah, thanks again for attending the seminar. Thank you, Paolo.
Bye-bye.
Bye-bye. Thank you very much.
Thanks.
Thank you. Nice meeting.
See you.